Hello everyone, welcome to another episode of the Organic Chemistry course. This is part 2 for A2 hydrocarbons. So under hydrocarbons, I want to talk about the chemistry of benzene. Benzene undergoes substitution reactions with chlorine and Br2. Benzene does not react directly with chlorine. It does not react directly with chlorine or Br2 and is unreactive towards any nucleophiles. If you go to the introduction of this course, I think I've shown you examples of nucleophiles, right? So benzene reacts with chlorine or benzene in the presence of what is called a halogen carrier catalyst, such as AlCl3 or Al-Br3. These are also called Friedel-Crafts catalysts. That's another word that is used, Friedel-Crafts. These are also called Friedel-Crafts catalysts, right? So let's say chlorine. Let's say we also have another Friedel-Crafts catalyst, such as Fe. Excuse me. Such as Fe. Such as such as Fe X3, where X is close to chlorine or bromine. So if the halogen in question that is reacting is Br2, the halogen carrier catalyst will have a Br3. If it is CO2, it will have a CO3 there. So now let's just go to the mechanism. Let's go to the mechanism. In the first mechanism, we've got the halogen carrier catalyst polarizing the halogen molecule to produce a partially positive bromine and another partially negative bromine. Then when the benzene comes in the next second mechanism, it helps to cause a heterolytic cleavage, breaking the halogen, right? Here you can see the halogen and the hydrogen, they competing for that position. Since the hydrogen is being ejected, you put an arrow like this to say it is the one that is being removed, right? Then from there you have a bromobenzene plus HCl plus the halogen carrier catalyst being regenerated, right? The halogen being regenerated. Now that's what that is what I was just explaining in the work that I just explained there. Okay. Now let us talk about the nitration of benzene. Benzene can also be nitrated using a nitration mixture. The nitration mixture contains concentrated sulfuric acid and nitric acid. Sulfuric acid is stronger than nitric acid and therefore protonates nitric acid. So in the mechanism here we have concentrated sulfuric acid plus concentrated nitric acid. Since the sulfuric acid is more stronger, it is the proton donor. It donates the proton, leading to the formation of NO2 plus, which is the electrophile, plus H2O. In the secondary reaction, we have this kind of electrophilic attack taking place there, and with the nitrogen NO2 and the hydrogen competing for that position. Since the hydrogen is being ejected, you put an arrow like this to show that it is being ejected. Then put it again there. Then here you have nitrobenzene plus an H plus. If you add all those equations together, you're going to find out that you will the catalyst with the catalyst, there's catalyst regeneration there that will be taking place. I think it will be fun for you to add those reactions together and see what kind of equation that you get. Okay, but what you're supposed to see, that the catalyst which is being regenerated is removed at the end of the process. So nitrobenzene is a yellow oily liquid. Reactions such as these take place below temperatures of 60 degrees, right? Now let us talk about methylbenzene. Methylbenzene is a CH3 group that donates electrons towards the ring, making the ring more negative and now prone to more prone to attack by electrophiles. So you must understand that methylbenzene is more reactive than benzene. So how is methylbenzene formed? Right? You have your benzene. Let me make a mechanism here. We have our benzene there reacting with the CH3, which is attached to halogen, plus a halogen carrier catalyst. Maybe let me just put XAL X3 there, leading to what? Equation like this, right? When I have my, let me say I will have my, okay, let me do this. Okay. Let me start over. Let me make a very a better mechanism. So in the first mechanism, I have my in the first mechanism, I have my CH3. Let me call it 1 there. Plus my halogen carrier catalyst, which is I produce my CH3. Okay, I produce my CH3 plus Al X4 negative. Right? As I go down the second part of this, I then add this electrophile to benzene. Right? I have my benzene there reacting with my CH3 plus. So the benzene attacks this, right? And I produce an equation like this. Right? Then the third part, I have my I reproduce that reaction, right? This and this in arrow there, plus my halogen carrier catalyst, right? Use my AlX4 negative to produce what? I then produce my methylbenzene on this side, plus my what? Plus my HX plus my AlX3, which is the catalyst regeneration process. So that's how methylbenzene is formed. Okay. So now let us talk about the reactions of methylbenzene. Methylbenzene is two sets of reactions. One, the substitution along the benzene ring and the reactions of the CH3 group itself. So I want to talk about halogenation here. That say you take a halogen, any halogen, right, chlorine or bromine, and that reacts with the methylbenzene in the presence of UV light. There's a substitution that takes place along the methyl group here. It's a free radical mechanism that takes place, right? You've done this before. Now, if you remove UV light and say the reaction taking place in the presence of a halogen carrier catalyst, substitution on the benzene ring takes place. As you see here, the hydrogen that was here has been removed, and it is combined with another bromine, and now we have bromomethylbenzene is the product that has been formed there. As for the naming, do you know about the nomenclature? I'll teach you the name. I'll cover. I think I will also connect this video to a lecture I did on the naming part there. Okay, now these reactions are examples of electrophilic substitution reactions. Now there's this reaction which is called the oxidation of the side chain. Okay, now under Cambridge standards, what they do, this reaction may take place in stages there. From methylbenzene oxidation of the side chain, for example, they prefer, for example, in the oxidation of the side chain there. Let me put it here. I have my, put a different color there, right? I have my methylbenzene here. Excuse me. They prefer to say this is my. They prefer to oxidize this using in potassium manganate and alkaline condition in alkaline here, right? And to produce COO negative like this, negative there, plus benzene at the first stage. Then if you add dilute acid there, dilute acid, any dilute acid then produces COOH group. Okay, so from Cambridge study, guys, that is the kind of setup they preferred. But in my notes there, I just simplified the reaction to say if just reflux under acidified conditions, you produce this, which is also equally correct. So they are just telling me, I was just saying potassium dichromate ions are weaker oxidizing agents than manganate ions, so dilute acid is used, right? Now I want to talk about the effect of delocalization, of electrons. Delocalization. Effect of delocalization of electrons in the benzene ring. So some groups, for example the CH3 group here, release electrons towards the benzene ring, making the ring more negative and more reactive towards electrophiles, right? So they are, for example, with the CH3 group here, it is an example of what is called an activator. So we have also have an OH group and an NH2 group. These are all called activators. They tend to push electrons towards the benzene ring, making the ring more negative. They are said to have a positive inductive effect. These cause substitution to take place on the ortho and the para positions of the ring, right? Now we also have species that are called deactivators. Another example here is COOH here, COOH, NO2, and their halogens. These are called deactivators. They tend to cause substitution to take place on the meta positions there, on the meta positions of the benzene ring, right? So that's all there is to it. Deactivators tend to withdraw electrons from the ring, making the ring more positive, causing substitution take place on the meta positions of the ring. So this brings us to the end of the part 2A2 hydrocarbons lecture. I hope you found this video helpful, and if you did and you'd like to support the channel, please comment, like and subscribe, and I'll see you all next time. Thank you.